Hey everybody, Ryan Shrout here with Intel, joined by my good buddy Tom Peterson.
Hey guys.
And that content you just got to see,
XeSS, baby.
so that was cool.
That was very cool. That is a very cool demo of a brand new technology from Intel called XeSS. I hope you've heard of it.
XeSS, it has been ingrained into my mind. We've been talking about it for quite a while.
It does feel like it.
It's really, so this video today, what we're going to talk about today is
XeSS. We're going to go deep into the technology. We're going to show some games, and we're going to kind of tell you some news about what's coming out next.
a little more geeking out than maybe we've done in some of the other videos.
A lot more geeking out than what we've done in some of the videos.
But
I'm going to try to keep it light, so don't worry.
Let's keep it mid.
We'll keep it mid.
We'll keep it mid.
We'll keep it
All
mid.
right.
All right, so let's dive right in. You know, to start understanding XeSS, we've got to start off by talking about games, right? So this is a frame of Hitman 3. And the way to think about it is when you're playing a game, you're actually watching effectively a movie generated in real time, right? So Hitman 3 will draw this frame, then I'll draw another frame. And that's when you see all these frame time charts, right?
Yeah.
But most people have not thought what's actually happening. Right? Inside that frame. Like when you're drawing this, there's mathematics that are running inside of the GPU, and we are actually going to generate mathematical instructions to generate each pixel.
Okay.
So let's take a look at that. So this is a visualization of what's happening inside that frame, right? This is running at 1080p, and you can see the blue on the bottom, that dark blue, that's floating point, and the stuff on the top, that's integer or other kind of exotic instructions, right?
Okay.
It's just like on a CPU, you run a lot of instructions, some are vector, some are matrix, and at the end of the day, you get a pixel. And those pixels are what draws the frame.
Okay.
All right. Now, this is 1080p. If you ran that same frame at 4K, or if you say turned on all the high settings, or if you turned on ray tracing, times get much longer, right?
Okay.
And that's why frame rates get lower. So on a single frame, it looks like this is about double the time, which means the frame rate will be about half.
Okay. Makes sense.
So we have a problem, right? Everybody wants to have good-looking visuals. You want to have high-resolution stuff, but you don't always want to have this gigantic GPU. You'd rather have regular-sized GPUs.
In a world where you don't have infinite free resources, how do you better utilize what we do have on hardware?
Exactly. So there's a whole area of research around here which is trying to figure out how do I take better use of the resources that I have on my GPU. And you're going to take a lower resolution frame and run some algorithm on it to generate a higher resolution frame, right? It sounds pretty good.
Sure.
Right. And now the trick is, can you make the data processing so efficient that the net result is better than if you had just rendered it high resolution?
If you just went back and rendered it different.
And so there's lots of different techniques in this space. You can say super resolution is one of these techniques. You know, maybe even super sampling is one of these techniques. They're all using kind of what I'll call classical sort of numeric models, where some engineers have gotten together, had brilliant thoughts about maybe how to do anti-aliasing differently, or how to like double a pixel size or something. But they're all limited by edge cases and border cases, and they're super complicated. It's like a race that never gets over.
Okay.
Now, what's changed is AI has arrived. Right now we have hardware that accelerates. You've heard
about this AI.
AI has arrived, right? So now some very bright people at Intel have figured out how to apply AI to this very same problem, right? So let's take a look at how AI works in general, right? So what I'm going to show you is what is AI. And then I'm going to tell you how it works inside of our graphics card.
Okay.
AI is using this sort of network of nodes, and they're typically called neurons. And what they do is they take data and they just run math on it, and they generate an output. So think of it as all these pixels, which is the input to this AI, are kind of combined, and then using weights that are learned, it generates an output pixel. But it starts off dumb. Right. So in this picture, I'm going to show you how training works, where we, in our supercomputers that are in the cloud, we run, you know, many cycles of training, and we iteratively generate an AI network. Okay. So the way it works is we take a low resolution image and a high resolution super sampled image. We run it on a forward pass through this network, and we generate an output. Now, initially that output is not great. It's got all kinds of artifacts. It barely even looks like a pixel. But what we do is we compare those images with the high resolution super sampled image that's a reference image, and then we calculate the errors, and we sort of back propagate, changing the weights as we go. And over time, run this on a lot of frames, on a lot of GPUs. Eventually, that network will converge. It's almost magic, but that network converges to something that will generate a high quality image.
Okay.
Yeah, and it's done so in such a way we take lots of different games, lots of different styles, so that when it's all done, this network works for games it's never seen. It's really impressive. It's the same way, say, Google does image searching or text searching. This is now being applied to graphics. So if you think about it, all of that sort of network relies upon mathematics. And in our case, traditionally that would have been built on what's called a MAC, which is a multiply accumulate. In this picture, we're showing how an inference might look, where we take 8-bit data and we do a multiply between two of these registers, and then we accumulate it into another register, and effectively that's the math, right? It's just multiply two things and then accumulate the result and keep doing it over and over. Okay. It's relatively inefficient for AI.
Okay.
That's why we invented a new technology called DP4A. What DP4A does is chops up that 32-bit register into 8-bit chunks. And by that way, we can now do 4 parallel operations, improving throughput by 4x. This style operation is available on a lot of our integrated graphics.
Right.
Now, we took it to the next level with XMX. XMX is inside of our matrix engine on our discrete GPUs. And in this world, you can see we're actually doing multiple of these multiply accumulates in parallel. So instead of doing one multiply accumulate and then writing an accumulation result, we're now running 8 of these in parallel, passing the accumulated result to subsequent stages. And that improves our throughput by up to 16x.
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 So XMX is a block, is a unit of the Xe core on our new Intel Arc GPU.
Exactly. We call it, the Xe core contains a vector engine and a matrix engine. Inside the matrix engine is this big systolic array that we call XMX.
Got it. And then DP4A, you mentioned, applicable to integrated graphics. That'll come up in our discussion a little bit later.
Absolutely.
But 16x seems like a lot.
16x is a lot, right?
That's
good. So that's the engine. So let's jump back to this frame of a game, right? So thinking about how would you take that mathematics and sort of get it into a game, right? It's not obvious. Like, you don't just take AI and like plug it in.
Sure.
Right? So what we actually do is you got to go back to how do graphics work. This is a pipeline diagram of a simplification, right? This is way more, it's way more going on than this. But imagine that you break down a simple pipeline into render, then you have some AI or some AA that's typically happening, and then you'll have post effects like the UI. So just breaking down the pipeline into that kind of simplicity, we can go back and take a look at this time chart, right? And now you can see the biggest section of this is all render, right? That time is render and pre-effects, and then you'll see a little bit of TAA and a little bit of post effects. So if you think about where do you optimize, you're going to go after this render stuff.
Yeah, makes sense. Yeah.
So let's think about how does that work with XeSS, right? Coming back to this pipeline, you can see that TAA slice right there in the middle. We're going to get rid of it, and we're going to put in our XeSS logic. Okay, we have an SDK I'll talk about in a little bit, but at the end of the day, we still do render, we still do post, but now because of XeSS, we can do a lower resolution render.
Right?
Okay. And if you go back to time, you'll see what it looks like, right? Here's our original picture, and now here is what it looks like when we run XeSS. Okay, diving right into it, that middle section is basically replacing that TAA calculation. And you can see that front part where it says render and pre-effects, that's a lot quicker.
Yeah, much shorter on this.
Much shorter. It's like half, it's not even half, right? That's because we're using a 1080p input render, and then XeSS is doing the processing to convert it into a high resolution image with high quality. It's pretty cool.
Yeah.
That last little bit is the post effects and the UI stuff. And you can see this is exactly like, if you were trying to figure out how does XeSS work, this is it, right? It's pretty cool.
Yeah.
Okay, but I'm simplifying a little bit, obviously, because that middle part with the purple where it's XeSS, it's actually running XMX instructions, which are 16x more powerful than everything else on this picture. So if I drew that to scale, it would kind of go off the chart, and you know, even a little higher than that maybe, and you would, you know, it just kind of gets crazy. So we're normalizing that back down to a reasonable.
I think the other version is a little bit easier to read. Yeah.
Okay. Yeah. So that's the bulk of the deep dive on the mathematics, right?
Okay.
But for you and me, actually, this is all about the game. So I
not
say,
just for you and me.
For everybody. For everybody, it's about the game. So let's go take a look at a couple games.
All right.
Hey guys, we're here with Shadow of the Tomb Raider. This is a developer build, so it's got extra options for us to play with. If you come down to the options setting, Ryan, you're going to be stock, and I am going to be the XeSS setup. So let's go ahead and get into the display and graphics setting.
Okay.
And right now you can see, hey, on my system, there's this XeSS option, and it's set at balance right now, but you can also see performance and quality and ultra quality. I'm going to go ahead and leave it at balanced, and I'm at 25 by 14. And you can even see down here under anti-aliasing, it says Intel XeSS, of course, because as we mentioned, XeSS does the aliasing for you.
Right.
Pretty cool.
And I'm at 25 by 14. Resolution, right?
Yep, and we got high settings on most everything over here. You can see
high and ultra on a lot of stuff.
ultra,
Yeah.
ray tracing is on. It's basically maxed out. Okay, so let's get back to the game.
Okay.
And when you're ready,
I'm ready.
3, 2, 1, resume.
All right, here we go.
I'm looking at a helicopter. I'm seeing 70 frames a second.
47, 48.
Okay, pretty good. And I am going to try and not die.
You can do it this time.
Okay, here we go. I'm running, I'm jumping, I'm at 65 frames a second. Game looks great.
44.
I am gonna turn right and go over this little jump right there. Looks good. Oh, there's a pole. Don't get electrocuted. Ryan, what are you seeing?
I'm low 40s as I'm going over the truck.
Low 40s. I'm at 65, 68. I made the big jump. I'm running down the hill.
All right, here we go.
Moving towards the burning electricity thing and jumping. Little building here. How you doing over there?
We're fine.
We're fine. Okay.
We're fine here.
Is that it?
We're done here.
All right, we're done.
Well, that was embarrassing.
That was embarrassing for
normal
you.
display of my
okay.
gaming capabilities for everybody to see.
Yeah.
But still good.
I thought it was great.
Very cool demonstration. XeSS on and off.
You saw all the options, right?
Yeah.
All the options, and you can see how people might, prefer to run with XeSS. They won't die.
Yeah.
Yeah.
Well,
and higher performance.
All right.
Yeah. So let's take a look at Shadow of the Tomb Raider and all those different settings, right? We talked
Right.
about ultra quality, balanced, and performance.
Okay.
And if you think about it, you might pick one option or the other, but you're going to get different performance, right? We're showing 47 frames per second is the base, all the way up to 89 frames per second in performance mode. Now, performance mode is going to be using the same network as balance mode, for example, but it's just going to be using a smaller resolution render.
Lower resolution starting input.
Exactly.
Into that model.
So you
Okay.
lower the resolution of the input to the XeSS model,
Right.
and then you do a more traditional upscaler, and then that goes into XeSS.
Ah, interesting. Okay.
It's very cool.
And so then we have these different settings, right? I think most gamers are probably going to look. They're very frame rate sensitive, right? So
Yes.
performance, balance, these are going to be the ones that we think
Yep.
Most people will default to,
Yep.
and the games will default to. But if you're very particular about
Turn on ray tracing, right? Turn on all your stuff.
yeah, but if you're very particular about image quality, maybe you do
Maybe just
quality
quality.
or ultra
And you
quality.
can-
You,
I
still
mean,
get
look at
big
this. Look at-
improvements.
20,
Going
30%
from
easy.
47 to 60 crosses that
Huge.
threshold.
That huge boundary.
That magical. You say it's not magical.
It
It's
is
very
magical.
real.
Turn on the VSync and you're going to get great results.
Yeah.
Yeah.
Very
Very
cool.
cool. All right. So let's talk about more games. It's
Not
all
just
about
that
games. Not just that one, right? Here is a collection of games that are already integrated with XeSS. And you can see the native frame rate on, say, Ghostwire is running at 25 frames per second. This is running 1440p with XeSS in performance mode. It goes up to 53 frames a second, right? So you get some really nice boosts. And you can see the amount of boost in terms of frames per second is somewhat similar, right? But let's go ahead and normalize this, and a deeper story emerges.
Yeah.
When you normalize this, you see that the frames that are most performance challenged, like in this case Hitman 3 or Ghostwire Tokyo, they get the biggest boost from XeSS.
So the games that are running at lower frame rates, more performance challenged
Right.
because of settings, right? You said you turned it on max settings, you got ray
whatever you want,
tracing on. You get the most benefit because you're
High quality
taking
shadows.
if we look back at those charts, right, the longest render times
Yep.
benefit the most from the
Exactly.
the inclusion of
Exactly,
XeSS.
because what we're doing is we're making the resolution that the render occurs at smaller. And if you make it smaller, it's going to be a lot quicker relative to these relatively long render times that are coming from high quality frames.
Okay, makes sense.
So let's take a look at the balanced mode. So balanced is, again, a little higher quality. It's going to use a little larger native resolution,
Right.
but you get great performance, right? 25 goes to 44. If you normalize it, you're talking a lift of 0.75, 75%
Yeah.
lift for games that are challenged.
Still very impressive.
Yeah. So look forward to a lot of titles. We'll talk about the title list in just a little bit. We did more than just these titles, though, right? We've been working with UL.
UL benchmarks we worked with to build an XeSS feature test that'll be part of 3D Mark in the advanced version. We've got a demo of it. Let's go take a look.
Okay, Ryan, so what are we looking at?
So this is 3D Mark. This is a developer edition. It's obviously one that has the XeSS feature test here enabled, right? This will be available when the graphics cards come out and when
Okay.
XeSS is available in games.
Very cool.
So everybody will get to play with it, right? So UL did a great job on this. This is a super cool benchmark. What we've got here is you've got two versions. You can run the benchmark and then you have Frame Inspector.
Okay.
We'll show both of these.
All right, let's do it.
You can set your output resolution, your XeSS mode, just like we talked about earlier, performance, balance, quality, ultra quality. We'll leave it at performance, running on a ARC A770. So we'll go ahead and hit run here.
Ooh, cool. All right, this is cool. So what are we looking at?
So we're running here. This is the native version without XeSS.
Okay, it looks like ray tracing is on.
Lots of ray tracing here. Lots of good detail.
It's like a future world here.
We're running under 30 FPS.
Okay, I'm looking at 29 on Riva Tuner. Same in the display here. XeSS is off. Okay, we're going to cut to the XeSS version and show the impact of turning XeSS on. Okay, we're back into the XeSS version. Ryan, what's going on here?
Same scene, same locations, right? Frame rates now well over 60 FPS,
higher.
into the 70 range, right? So
Yeah,
we're seeing
that's
significant
like
performance increase on this.
And the quality looks great. I mean, I can see ray tracing is on.
I would say the image quality looks noticeably better, less shimmer, less kind of artifacting across it for sure.
That's wild, because actually XeSS on looks pretty good to me, like better.
Yes.
All right, Ryan, this is the results screen. What are we looking at?
So results here show, XeSS off averaging just about 29 FPS, XeSS on 69 frames per second, 138% performance
That's
uplift
more than double,
on
right?
this result. Yes, yeah, more than double. So impressive performance results. But I also think the other cool thing about this feature test is the frame inspector.
Okay.
So I'm going to go ahead and start this.
All right.
This basically lets you pick your XeSS mode, how many frames you want it to render, and what frame of the benchmark you even want it to start at.
Okay, and
right?
you want to do performance here.
Yeah, I would set it up for performance here as well. What this is going to do is allow users, enthusiasts, press, anybody that wants to just see it, really compare exact side-by-side frames.
You don't need a capture card.
You don't have to have any fancy capture equipment to do it.
Okay, well, why don't we cut to the video of the run itself.
So you can see here it's rendering its images, obviously not indicative of the frame rate. It's saving those files to the hard drive.
Cool. And now it's going to rerun it with XeSS on, right?
Right.
That's cool. Okay, so we're back, and I see the numbers are looking higher, but that's not the point of this one. The point of this is to look at the quality.
Look at the stills.
Yeah. So we're going to see the stills.
So I'll go ahead and make this full screen. So now this is a really cool tool where you can compare on the left the native rendering with TAA, and on the right XeSS.
Wow.
In performance presets. So it's cool. You can scroll around these the stills, and it matches it. You can actually look through all 10 of the frames that you rendered.
Very cool.
And you can obviously go to anywhere in the benchmark here and kind of do this. And it has the ability to kind of zoom in and here's a 2x zoom and kind of compare the.
I'm kind of getting the idea that the quality is actually higher on the XeSS one.
It definitely looks better, right? Like if you look at these columns here, you can see kind of the
edge details,
the jaggedness here, and some of the smoothness.
It's
that
actually
comes
less noisy on the right too. And that's weird, because I really would not expect that.
It's very cool, and maybe you can go around here and you can zoom in to 4x and kind of compare some of the stuff. Maybe the most interesting part to me here, though, is the fact that even though we're in this incredibly futuristic, space society, there's still a janitor's cart with.
Nice. How do we do on accelerating bottles?
Yeah, no, the image quality of these spray bottles
That's terrible on the TAA side. On the XeSS, we rock on bottles.
Yeah, very cool.
Fantastic.
But a great tool for people to play around with.
Yeah, but the funny thing is XeSS is all about performance, really, right? So getting better quality and better performance, that's pretty amazing.
Seems like a win.
All right, well that was pretty cool, right? We're showing good performance lifts. You can play with the quality settings. I think people are going to play with that a lot.
I think reviewers, I think enthusiasts, people that are just like interested in the technology of this are really going to love, not only to see the on and off performance delta that the benchmark easily enables you to see, but looking at that frame analyzer tool is something that's really difficult to do normally.
It's very hard to do, and you can get in there and kind of really see what do you like and what do you not like. Right?
Now, it's worth pointing out, we got the performance data on the slide now, 2.5x. Very high.
Very high. And again, this is probably about the best case for XeSS, because that has ray tracing on. It's got very complex models. It has a long render time. And remember, long render times are where XeSS really shines. Right?
Okay.
So this is probably a little bit more than we would expect to see typically, but it's all real, right?
Very cool.
All right, so let's continue along back to XeSS. What I really want to talk about a little bit is, how does this algorithm really work? We talked about how the model gets trained, but how does that model get plugged into a render pipeline?
Okay.
Right? So let's take a deep dive into the render pipeline. I already showed you this picture where XeSS is kind of plugging into TAA, right? Well, what's that XeSS block doing? It's pretty simple, right? At the end of the day, we're going to take a low resolution rendered frame coming out of the traditional render pipeline, and we're going to combine it with motion vectors, which tell us, where are things moving, because that's very important to kind of predict upsampled images. And we're going to combine that with prior frames that have been already generated. The cool part about this is, on the camera, we're actually jittering the camera around to generate through successive frames, more samples, more data, right?
Okay.
And we can feed that data back in to the XeSS pipeline effectively to generate a single super resolution image. Makes perfect sense, and it seems pretty straightforward. What
I
have been
mean,
working
look,
on it for
there's
so
some
long.
boxes there. It makes
There's
sense.
a little engineering here as
Flow
well.
charts and stuff.
Yeah, I think it looks pretty good. So I also have a cool animation that will show you how this looks in action. Okay. So that thing in the middle, that's our neural network. And what we're doing is we're taking low resolution frames and pushing them into the front along with motion vectors. We're generating a super sampled image that we're feeding back into the frame history for subsequent super sampled frames. And also at the front, we're jittering the camera.
Interesting. So that super sampled frame goes out to your display.
Yep.
That's what you get to see. Goes into this buffer.
Yep.
Reutilized for the next step of
frames,
the AI
right?
algorithm.
It turns out that as you're moving the camera, there's a lot of information in the frame that you're generating. So use that as information to feed into the network. Pretty cool idea.
Very smart.
Anyway, our XeSS software stack. So obviously we got to enable our ISVs, and we do that through this XeSS SDK. It includes a whole bunch of software that makes it easy to plug in, and it plugs in effectively using the same interfaces that, say, TAA did. So if you have a game that was written to use TAA, which is a lot of them, plugging in XeSS is actually not that difficult.
Okay.
Now, we do optimize kernels using a low-level language to optimize for XMX. So as part of this XeSS SDK, you're going to get great performance on our XMX-oriented ARC GPUs. But we also do separate models to support DP4A.
Okay.
So think of it as these are using a different architecture. It's got different amounts of sort of complexity, but you still get great results. And that's primarily targeting our integrated graphics.
That's maybe not initially intuitive that something that's, seems very compute intense would be coming to integrated graphics, but it actually, this is an area where you're probably the most challenged in terms of performance, the longest render time.
You're absolutely right. I mean, integrated graphics, a smaller XE core count means you're going to get longer frame times, which is the perfect place to say, hey, let's render at lower resolution and then use this other algorithm to make it faster.
Okay.
Now, it's not just our integrated graphics. We take that same model and make it available to other GPU vendors. So effectively, think of it as if you have a non-Intel GPU, you can also get XeSS support.
Oh, interesting. So we would expect people to be able to run XeSS on NVIDIA and
AMD. Yeah, depending on what the ISV, what the software, what the game developer does, XeSS does work across multi-vendor GPU.
Okay.
And that's a big reason why XeSS is being so quickly and easily adopted, right? This is not just a technology that runs on Intel, it runs on other people as well.
Interesting. Okay.
So let's take a look. We've got lots of different titles coming for the XeSS launch, which is going to be coincident with the introduction and the availability of our discrete GPUs. No surprise.
Seems to make sense.
Yeah, makes a lot of sense.
In this slide here, we're showing 20 different titles, right? These are 2022 games. Some of these are already out, where XeSS patches will come out, or the game isn't out yet. When it comes out, it'll have XeSS support. So I mean, this is a great start for us.
It's a great start.
There's more titles coming.
Our DevRel team, our Dev Tech team, this is just an amazing outcome. But there's more. As you know, we have a huge title coming with XeSS at launch, and it's going to be Call of Duty Modern Warfare 2.
Yeah, so this is great. So when this game is released later this fall, it will support XeSS on day one, right? And that's, I think, maybe the best-selling title 22, one of the best, if nothing else.
Are you any good at it?
I'm still not any good at that game.
But we're going to have a great time with it. And it's a fantastic title. Getting XeSS into that title right now is just a big endorsement for the tech.
Very cool.
Yeah. But it's not just about 2022 games, Ryan. It's about 2025, right? And so right now, we're already working with this game, Instinction, which is made by Hashbane. And it's a really cool game, dinosaurs. It uses great technology. And we've actually reached out to the developer to see what they have to say about XeSS.
Our team has been working closely with Intel, and we're very happy with the results we've seen by integrating XeSS into the game. This is the first instance of UE5 running on Intel Arc GPUs, and the first UE5 title running with XeSS implemented. We are proud to show you how this technology is shaping the world of Instinction. This has allowed us to implement UE5's Lumen and Nanite features, adding more natural and vibrant lighting to the world of Instinction, whilst ensuring that the environments, animals, and characters you're encountering are at the highest possible fidelity. The integration of XeSS technology was easy and gives us a great level of performance to deliver a fantastic experience. This is just a taste of what's to come from Instinction. Instinction will be able to be experienced at its highest level on Intel Arc and will be released in 2025.
So Instinction's really cool, right? 2025, it's using all modern technology. It's based on Unreal 5. It uses Nanite and Lumen. So it got great lighting, great geometry. It's going to be a really pretty title.
And I think it's important for people to see our commitment to Arc, to this technology, working with developers on far future titles.
Far future titles. I mean, dinosaurs are always going to be fun, but it's effectively a testament about how long-reaching our investment on XeSS.
Yeah, agreed.
Yeah. So let's wrap it up.
Okay.
XeSS is a brand new technology from Intel. It fuses AI with render to get higher performance. Starting out, we looked at a bunch of different titles. I see 40% all the way to over 2x. It's really just an amazing technology, and I can't imagine anybody, where enabled, won't turn it on.
Now, what about other applications of AI? We've talked before about, hey, this is just the beginning of things.
Yep.
What else?
Well, this is honestly, Ryan, just the beginning. I mean, AI is changing everything. It's changing every industry, and it's just now starting to intersect with render. So, people have talked about, hey, what about noise reduction? What about lights? What about geometry manipulation? So there's all kinds of likely candidates for AI applied to gaming.
Very cool. So thanks everybody for joining us. Thanks, Tom, for coming in and explaining all the details of XeSS. Arc.intel.com. That's the URL where you'll find this video, all the other discussions we've had about features, capabilities, and performance. We've got more content that we're still planning to build and put out into the world.
Lots of stuff.
Ray tracing, overclocking.
Board breakdown.
Our board breakdown, and talk about some of the cool factors
screw
there.
count for Steve.
Screw counts are very important. They're very important. So arc.intel.com. Stop by there, and thanks everybody for joining us. But before we send you out, we'll pass you along another video of some other great XeSS titles coming out this year.
Beautiful game, by the way. Jump over that pole, through the water. I think ray tracing is on. The settings are at high, basically.
Yes.
It all looks great. Oh my God, I just died. That was an amazing gaming effort there. Fantastic. I am coming through. I'm jumping across.
Gorgeous looking.
I'm at 68 frames a second. I'm running through the water.
I'm in the low 50s.
Okay, 71.
45.
By the way, ray tracing is on. All the effects are set. Oh God. Same place I died. God damn it.
Man, brutal, huh?
All right, let's do it again.
Oh, wait, no, we don't want to use this one where you're the one that dies?
Maybe we do.
Save this one for outtakes.
I don't know.